All right, let's talk about the concept of pKa and how it relates to strength of acids, particularly organic acids. I don't know how much you guys remember from your chemistry, from your principles of chemistry class, but you would have gone through some material about acids and bases. And one of the concepts that you would have touched on was the concept of Ka and pKa. So the Ka that you would have seen first was the acid dissociation constant, a measure of how strongly or how well your acid dissociates. The more it dissociates, the stronger it is. What that meant was the higher the Ka, the stronger the acid. All right, Sa for stronger acid. And you would have also seen this formula which relates Ka and pKa, and if you don't remember it, well, take a look at the relationship here. It's very similar to the pH is negative log of H plus here. There is a negative log relationship, which actually means that these are inversely proportional to each other. What that means is as the Ka goes up, as the acid strength goes up, the pKa value actually goes down. So what that means is if you're looking for the strongest acid possible, you're looking for the one with the lowest pKa you can find. All right. So when we look at this table of acids, you can hopefully apply that and see, well, if this tells me what my pKa's are, I can see just by looking at it which acid is the strongest, and of course it's the HCl because it's got the lowest pKa value. All right. So when we look at this table, let's take a look and see what this actually means. All right. Notice that there are two arrows in the table, one going up labeled for the acid side and one for the conjugate base side. Notice that when you go from bottom to top, the acid strength goes up in this table. And notice that that correlates to this pKa set of values. We said before that the lower the pKa, the stronger the acid. Therefore, the HCl is the strongest acid. The methane on the bottom is the weakest acid with the highest pKa. When you take an acid and remove the proton, you get the conjugate base. And these acid strengths and conjugate base strengths are actually all inversely proportional as well. If you have something that's a really strong acid like HCl here, really strong as measured by the -7 pKa, that means it really wants to donate its proton, meaning the Cl- is really stable and non-basic. So when you look at this arrow here, you'll see the base strength increases as you go down the table. So when you go down, the base strength increases as the acid strength decreases. All right. So the relationship here is a strong acid gives a weak conjugate base. And in the same way, something that's a really weak acid, and it's very difficult to remove this hydrogen, gives a really strong conjugate base. Okay. All right. So let's apply what we've just been talking about to answer this question. Which base is strong enough, and when I say which base, I mean which base from this list. Which base is strong enough to deprotonate H2O? Now what does deprotonate mean? Well, of course, deprotonate means to remove the proton from the acid, from all these acids to the conjugate bases. But we're looking at particularly H2O. So I'm going to put a line here. All right. This is our cutoff point. All right. Take a look at the pKa's, and you'll notice as you go down, the pKa's of the acids get higher and higher, the acids become less and less acidic. The conjugate bases become more and more basic as you go down, as you would expect in opposition to the strength of the acids. So when you deprotonate H2O, you get OH minus. All right. So when we have our H2O here, and we add in some sort of base to remove the proton, we get OH minus. And so the question that's being asked up here is, which of these bases can remove this proton to give OH minus? And whether this data is in the form of a table or just a list of acids with pKa's, here's what you want to look at. All right. The fact is that any base that's stronger than the conjugate base of what you're looking for, in this case water, is going to be strong enough to deprotonate from that particular molecule. So in the case of water, any base in this table that's stronger than the conjugate base of water will be able to deprotonate this water. So for example, according to this table, all of these, this guy, this guy, this guy, this guy, this guy, and this guy, all are stronger bases than the OH minus. Therefore, they will all be able to deprotonate H2O. Now, if you didn't have this information in the form of this nice table, what if all you had was these acids and their pKa's? Well, all you'd have to go off would be these pKa values right here, all right? And you would know that the pKa of water is 15.7. So any acid whose pKa is lower or is higher than that of water will have a conjugate base strong enough to deprotonate it.